Good morning, good afternoon, everybody. I'm Tom Rippinger, Marketing and Communications Manager for DSM Engineering Plastics in the Americas region. Thanks so much for joining us for today's webinar. I'll be your moderator for today. First and foremost, we wish all the best. Hope your family is doing well and you're staying safe in these challenging times. Today we're going to have some opportunity for you for live Q&A at the end of the presentation, so please use the chat functionality on the right-hand side of your screen to submit your questions throughout the presentation, and if we don't get to them, we will follow up via email following the presentation. So without further ado, I'll introduce today's presenters, Jippe van Roten and Bill Senge. Thank you.
Well, maybe as a first quick introduction of me, my name is indeed Jippe van Roten. I'm an advanced development manager at DSM, looking into mainly automotive applications, and bearings is one of the fields that I'm looking after.
And hello, everyone. My name is Bill Senge. I'm a marketing manager here at DSM. Been here about 15 years, and excited to be doing this with you today. It's a very these are strange times, and it's a very different thing for us to do, but happy to stay connected with our partners, with our customers via this webcast. This is the first of a series of webcasts, so I'll let you know there are further webcasts coming in the next couple of weeks in automotive, on electronics, and on hot charged air ducts, but also outside of automotive, in shoes and in food contact and electrical distribution. So I welcome you to attend as many as you might like to see. The intent of these are to be quick hitting, 15 to 20 minutes in nature. And today's topic is high-speed bearings. So I'm going to turn off my webcam and we'll get into the presentation. Yeah, so our agenda for today regarding high-speed bearings, we want to give you some insight as to some of the current plastic materials used in bearings, specifically the cages in bearings, and our successes in recent years in that space. There's a key trend that's changing the space, electrification. We're going to spend some time understanding what those changes are, and then how DSM in particular is addressing those changes with the development of high-speed bearings. We're doing work in design and modeling. We're doing work in molding simulation, as well as some new and innovative materials in use. And we'll end with Q&A. So to start, material positioning in bearing cages is actually quite simple as it relates to bearings in both automotive and outside of automotive. Nylon 6/6 is certainly the primary material used in a large majority of bearings, specifically the unsealed bearings. POM has a small share in non-automotive and such things as appliances. It's more about building the entire bearing itself out of POM, not just the cage. But we'll focus on 6/6 today. There's a point at which, from either a stiffness over density perspective or a temperature perspective, possibly fluid exposure, that would drive you into some higher end materials. Failure modes that happen as a result of those include stress failure, in addition, centrifugal deformation. So as these bearing cages are spinning, they deform based on the mass associated with the bearing. When all that occurs, you tend to move into higher products like Stanyl. We have a couple of base grades, TW200F6 and TW261F5, also a TQ version in Asia, that are used when 6/6 clearly won't do the job anymore. There is a point, due to fluid exposure primarily, that even Stanyl isn't enough. And you'll see PEEK used, quite an expensive material in both glass-filled and carbon-filled varieties. And when a bearing manufacturer has really no other alternatives, metal is used quite a bit. In unsealed systems in particular, metal is quite common. In sealed systems, the weight of the metal makes it less than ideal. to build on that a little bit, it seems like a simple flow of materials, but in reality, it does get quite complex. The effects of temperature, the aggressiveness of the oil that is chosen, often these are lubricated with either oils or even greases. The particular choice of that grease can drive you towards one material or another. PEEK is fairly inert to most of these fluids and greases, but only up to 150 degrees Celsius, and that's a key point as we talk about electrification and higher speeds, that that 150 degrees limiter really does become a limiter in this space. Here's an idea of some of the areas of traditional success that we have in Stanyl, understanding that, yeah, the words there are quite small, it's kind of hard to read. But my intent is for you to see, number one, that you see that we make a bunch of different designs of bearings. So whether it's angular contact ball bearings, needle roller bearings, even tandem ball bearing applications. Most of these are used in the drivetrain of an internal combustion engine. But additionally, outside of that, we do have experience and success in a hub bearing cage, as an example, for a front wheel, primarily due to the fact that Stanyl is a material that really flows quite well. Now, what all of these applications really share are a couple of things, and the value that our customers get from our materials are these. One, a clear cost savings versus PEEK. We all know the expenditure for PEEK is in that $40 to $60 a pound US range, depending on the variety and what's in it. Metal also machining quite expensive as compared to standard injection molding. Additionally, some clear weight savings versus metal, and that provides efficiency for the bearing. Additionally, Stanyl resists quite a bit of the fluids used for cooling and lubrication, and even in high temperatures required in those environments. The extraordinary flow of a linear molecule really allows for the smallest packaging sizes. We can make the walls of these bearing cages really thin, but really from a user standpoint, what we offer is the proper combination of what I'll call stiffness and toughness. Now, from a stiffness perspective, you need the bearing cage to keep its shape for bearing performance, so that the metal elements remain in the track where they're designed to be. But at the same time, the material has to be tough. You can't have a super stiff plastic without toughness for two reasons. One, it becomes really hard to demold the part when you're taking it out of the injection mold. It can snap and break before you ever use it. And second, for the insertion of the metal elements, there's a sort of an expansion and quick contraction that has to occur when you're snapping these bearings into place. So there has to be some degree of elongation in the plastic, and the success of Stanyl in the space is really based on that proper combination of stiffness and toughness in various environments. Now, moving into high-speed bearings, the electrification specifically of the powertrain, but again, also outside automotive, electrification really changes the game for a bearing. E-mobility simply demands higher power, and that power either comes from higher current, which shows up in torque, or it comes from higher voltage, the speed of the shaft on which the bearing is spinning. That voltage drives that higher shaft speed. We've gotten quite a bit of feedback from the industry in terms of what that means. Yeah, it's measured in NDM, N being the speed, and DM being sort of the ratio or the average diameter, internal versus external of the bearing. The numbers you're seeing there are something in the neighborhood of 40 to 60% higher than what we see in standard bearings. What does that mean? Number one, it increases the need for better stiffness over density. The faster it's spinning, the heavier the bearing is, the more of a problem it is, and it causes more deformation. Two, the fact that it's spinning increases operating temperatures. Third, with the increased operating temperature, you will see additional chemical resistance required. Different oils and greases may be required for these faster speeds because of the higher temperatures. And then finally, electrified cars simply last longer. So aging, specifically as it relates to lifetime, also the game has changed. So how's DSM managing this? Yeah, in three different ways, really. Number one, we're doing quite a bit of work in terms of modeling bearings and understanding the performance. In the upper left there, you see two models where we're trying to optimize bearing cage designs for weight. That's crucial in order to gain centrifugal benefit, so less deformity for our customers in this space. Second thing we're looking at the effect of stiffness when the bearing is rotated at a particular speed. So that aids us in material choice. We have a variety of materials we can put into this space of varying thicknesses and stiffnesses, and we need to understand what does that additional stiffness mean in terms of improvement of the displacement of the bearing. Third, we need to analyze these higher speeds. So once we've modeled and optimized the design, once we understand what grade we're best positioning in the space, we have to understand at these higher speeds in both the original designs and the modified designs, what does that mean in terms of displacement at a variety of speeds. Our customers don't all need the same speed, so we need to understand it across the entire range of speeds for the space. So our goal here is really to provide a complete portfolio of materials with good quantitative modeling to really predict the application performance before we start cutting tools. Really important in this space, I think, to get first time right, as this is a new space for a lot of our customers that manufacture bearings having to deliver for electrified drivetrains. The second thing we're looking at much more in depth is advanced mold flow techniques. So what you see here are two different mold flows. You look at that cage on the left, it's a needle bearing cage, and it's a fairly simple looking cage. And for those of us who have done enough mold design and processing in our lifetimes, it would seem that one gate would be sufficient for such a design. I can tell you in this case it was not. What happens in that design is that you see what I'll call a backfill condition, where the material gets to the bottom of the cage and then wants to fill back up. So what you're creating there are a bunch of weld lines that you don't want. Now, why are weld lines, where the two flow fronts come together, bad? Because that's where the failure tends to occur at these, whether it's in low speed or high speed bearings. The failure in these products are going to occur where the product is weakest, and that's simply at where all these weld lines occur. Our goal in optimizing and understanding using mold flow is to minimize the number of weld lines and to put those weld lines in a place that is less critical versus more critical. So in the case of this design, 3 gates did the trick and put the weld line in a place where it was less critical. In other designs, it might be putting it in the thickest part of the bearing, where it's the safest in terms of strength. We can easily do this with internal technology. Our mold flow people are stationed all around the world and well versed in minimizing weld lines in this technique. So you've seen 2 things we're doing in terms of simulation. We're also using materials in this space to try and sort of push the innovation limits for our customers. Understand that there's, with these higher speeds, you're going to see a shift away from nylon 6/6 into the higher performance materials. We need to be prepared for that with advanced technology. We're offering one new grade called 4TMX50SP. That grade is significantly improved in chemical resistance versus the standard Stanyl alternatives. So we're targeting with this grade really for bearings that need fluids with which Stanyl doesn't have the proper resistance. We've really had to dial that grade in to optimize the stiffness and toughness. I'll say that a PPA style grade versus an aliphatic nylon grade, it's much tougher to dial in that stiffness versus toughness, because typically PPAs lack in toughness to some degree. Where fluid resistance is okay and we need next generation stiffness for higher speeds, we're offering carbon fiber grades in Stanyl, which haven't been common in this space, but are becoming much more common based on some of the stiffness requirements we're seeing, as high as 10 gigapascals for customers in some regions. What's nice about Stanyl versus other materials in the space is its high flow capability, so we can get really thin walls and maintain that stiffness required for the application, and it's a huge cost down versus the carbon fiber filled PEEK alternatives. Now, there are going to be some cases where we have nasty fluids and we need next generation stiffness. We've developed another new material for that called 4T-ACE P1100P. So it sort of combines the advanced fluid resistance of the MX50 SP with the flow and package size capabilities of the Stanyl TW200B6. Again, a decent cost down versus carbon fiber filled PEEK. And when I say decent, I'm talking in the 50 to 70% range at a material cost. So I showed you this diagram earlier. This is sort of the material flow as our customers would hope to choose materials in this space, and we've inserted those two new grades, the MX50 SP and the P1100P, as well as the Stanyl TW200B6, in sort of a flow chart if-then diagram. We hope that our customers would move from 6.6 to Stanyl quite easily, quite readily, but we can guide them certainly on the extreme temperature fluid cases, which push you towards the glass-filled grades first, and then the extreme stiffness and density grades in both Stanyl and 4T carbon fiber filled. In closing, I want to try and impress upon you what I hope for you to take away from this presentation. Number one, that electrification has really changed the landscape in bearings, and these high speeds require new upper limits for performance, specifically stiffness, and require a much more critical view on deformation of these cages as they spin. And additionally, that DSM is really taking a three-pronged approach to try and extend these capability limits. And our goal really is to save money versus PEEK and metal for all of our bearing customers. One, choosing the right material first time, using modeling deformation based on speed and temperature. Two, to place minimal weld lines in the safest areas using our advanced mold flow simulation capabilities. And three, to apply the right new material technology that continues to support cost down initiatives for bearing manufacturers and users while upping the game in terms of performance. Folks, that's what I have for you today in terms of content. I promised quick hitting. That was, what, 17 minutes. We'll open the channel now for questions. I'll reach out to Tom. He's been sitting online. If you've typed in any questions, he can give them to both Yipa and I, who will be available for those. So, Tom?
Thanks, Bill. Yeah, like he said, we're going to go ahead and open it up to Q&A. First question for you. You talked a lot about new materials during the presentation, particularly Stanyl and 4T. Could you just briefly describe the key difference between Stanyl and 4T for these applications?
Sure, I can do that. Chemically, the difference between Stanyl and 4T is pretty simple. Stanyl is a nylon 4,6. It is a straight chain molecule, so similar to a 6,6 in sort of design, but much different in terms of performance because it crystallizes really fast, and it's a sort of a symmetric molecule, makes it quite easy to work with. 4T is also a 4-based molecule, similar to Stanyl. However, it has a PPA backbone in it, so a large benzene ring is part of the chain. So what does that afford you? That affords you, improved dimensional stability. That affords you some chemical resistance, certainly. What you sacrifice is flow capability, and crystallinity. That's the primary differences between the two. You need both in this space because you need so often to really minimize the packaging space. You need Stanyl for its flow perspective. It's kind of, you know, you picture two molecules and one has a big benzene ring attached to it, dragging it along. It's tough for that molecule to fill the thinnest of walls. So we would certainly position Stanyl in cases where customers are aggressively trying to design. On the other hand, where we're coming up with new oils and greases that Stanyl doesn't like, as an example, Stanyl tends to not like acidic fluids. We position 4T in that case.
Thanks, Bill. We've got one from Ashwin Kukredi. How's the processing of Stanyl with hot runner molds?
That's a great question. It's quite good. Residence time is something you'd want to be conscious of as compared to a 6.6. So you have to include a hot runner tool as part of essentially the barrel of molten material. So when calculating residence time, we would hope for, say, 4 minutes maximum. You get good control at the hot runner tips. Often you'll need, if you go with just simply a hot sprue design, you'll want a reverse taper nozzle, which is common for nylons, but that's crucial to the design. Yeah, the material sets up quite quickly, so I would recommend certain brands of hot runner tools over others to work with Stanyl.
Thanks, Bill. This might be a good one for Yipa, this next one. Jason asks, what are the typical oils and greases used in the bearings? Do you work with fluid suppliers to optimize system performance?
Yes, thanks. Thanks for that question. That is indeed an excellent question because the chemical resistance basically depends on the lubricants that are used, and there's a plentitude of lubricants, and well, these are packed with kitchen secrets. I mean, everybody is proud of the lubrication capabilities, but nobody's willing to lay bare how they get that great lubrication qualities in the recipe. And it's so we know that some oils are more aggressive than others. Typically, the engine oils are very benign. Some of the automatic transmission fluids can be benign, but can also be more aggressive. Hypoid gear oils, typically with loaded with extreme pressure additives, are more of a challenge for polyamides in general. Those would be the open bearings, which are lubricated by the splash oil or oil mist in applications like transmissions, etc. Then there's a very big segment in the market in sealed bearings, which are sealed for life, which have a grease, typically that is being packed in, and that is a big spectrum of lubricants. To the specific question, yes, we are collaborating with key lubricant manufacturers to be able to see what the next generations of lubricants will be bringing, and to stabilize our grades, our plastics, in accordance to those. That would be my response for now. If there are more specific questions, please reach out to us at DSM.
Thanks, Yipa. I have a question from Michael. What are the disadvantages of metal cages over plastic in terms of internal friction in bearings?
I can take that question. The big disadvantage of metal bearing cages is that if they fail, they tend to block the bearing. Because these chunks of metal, the debris that basically remains if the bearing cage falls apart, could get stuck between the roller elements and the bearing races, and they could jam the bearings. And this is why metal cages are very capable, but they do have this blocking catastrophic failure mode. Plastic bearing cages, if the cage breaks or if a roller element breaks, or a roller element causes the cage to break, these plastic fragments from the bearing cage would be soft enough to be basically ground up between the bearings, the rollers and the races. So that is a very important argument to choose in favor of plastic bearing cages.
Thanks, Jippe. Another one from Ashwin. How do the new grades of Stanyl provide internal lubrication to the bearings?
I can take. You want to take that one, Jippe?
Well, I can start.
Yeah.
Typically, for these bearings need to be lubricated. So adding internal lubricants, isn't really called for. I mean, if the lubrication is starved for the bearing, then the bearing will be extremely short-lived, and you won't be able to extend that bearing life with self-lubrication of the bearing cages. There is also the thing to stay away from, the condition to stay away from, would be that cage deformation impinges on the rollers and scrapes off the lubricant, because the lubricant is needed between the rollers and the races because of the geometrical shapes that induce some part of sliding in the contact area. So internal lubricants basically are not called for, and the space for that you would want to sacrifice for internal lubricants in the plastics would be better used to beef up stiffness and strength of those plastics.
Yeah, and I'll follow up there. Should your application, whether it's a bearing, I think unlikely for a bearing, but in any application, require that internal lubrication. We have a wide variety in our Stanyl and 4T portfolio of materials with internal lubrication. They're typically used in such markets as gears, where you're seeing a lot of regular wear-related contact, and designed with various glass contents in it for different requirements. So we have those materials available, but I find that it'll be unlikely that you'll, at least in applications that we're aware of, need them for bearings.
Thanks. I have one last question from Sagar. How does PA4T performance compare in chemical resistance versus PA6T?
4T in general outperforms 6T, 9T, 10T in terms of chemical performance, chemical resistance. And it's really about that 4 chemistry. In terms of crystallinity, the 4 chemistry allows for a higher crystallinity in general in 4T versus the 6, 9, and 10Ts. That crystallinity combined with the benzene ring associated with all PPAs really optimizes the chemical resistance in favor of 4T. 4T would absorb slightly more moisture than the PPA, but negligible, especially in such applications as this one.
Thanks, Bill. Well, with that looks like that was our last question, concludes our Q&A. Thanks so much, Bill, Jippe, for a very informative presentation. Those of you that ask questions, we'll be sure to follow up via email with you just to make sure we adequately answered all of your questions. And this is the first in a series of free webinars that we're going to be offering in the coming weeks. So encourage you to join for any and all other topics you'd be interested in. If you visit dsm.com/plastics, and go to our blog or take a look at our LinkedIn page. We'll be sharing the schedule of upcoming free webinars. Thanks so much for attending, for joining us today, and hope you have a great day.